Hello everyone, my name is Ahmad Rezahiai. Today I would like to present my work about robustness implies fairness in the causal algorithmic recourse. The work was done in collaboration with Amir Hossein Karimi, Bernard Sholkov, and Setare Mahsoudi. Before stating the main result, let's quickly review some definition and previous works. To better understand this concept, let's start with the common real-world example. Bob, an AI researcher, is seeking a loan to purchase a home. However, his loan application gets rejected by the bank, which uses binary classifier. After he identifies the reasons for the rejection, the primary question is, what should I do to get a loan in the next time? Causal algorithmic recourse provides low-cost recommendation to individuals who have experienced unfavorable outcomes from automated decision-making systems based on the causal structure in the feature space. Before diving into definition and the results, let's first establish our data model. In our data model, M represents a structural causal model or SCM. G is a directed acyclic graph that describes the causal relationship between parents and children. X denotes the endogenous or feature random variable. U represents a set of independent noise or exogenous random variables. F describes the causal relationship between any endogenous variable xi is direct causes parents and an exogenous variable ui by means of the deterministic function fi. S represents the mapping between endogenous and exogenous spaces, which is achieved through the function f, and S minus is its inverse. H is binary classifier. The cost function quantifies the expense associated with taking certain actions or modifying the features. F represents the set of feasible intervention. Finally, XCF represents the counterfactual of instance X with respect to action A. In the upcoming slide, we will use a simple example to show the main ideas. The model consists of one immutable sensitive attribute A and two manipulated continuous feature x1 and x2. We assume that the classifier is linear and the cost function is defined as the L2 norm between an instance and its counterfactual. As can be seen from the figure, causal algorithmic recourse refers to the process of identifying the optimal action that modifies the result of the classifier by an action A that replaces the value of the subset of features with the theta. We also define the recourse cost as the cost of the optimal action. Similar to many algorithms, fairness and robustness are two important properties that enhance the deployability of recourse in the real-world problem. Robustness refers to the ability of the recourse recommendations should remain valid under a small perturbation. To define adversarial robustness, we need to build perturbation set. In Dominguez's papers, the authors first define a perturbation ball centered around the origin with a diameter of delta. Then they calculated causal counterfactual by additive intervention to achieve the counterfactual perturbation around X. The adversarially robust recourse problem is about finding the most cost-effective recourse action that is resistant to adversarial perturbation. In other words, a recourse is considered adversarially robust if it does not only shift X to the favorable region, but also ensures that all the values inside the counterfactual perturbation ball are shifted to the positive region. Now, let's define fairness. There are different notions of fairness. The two main types are group level and individual level. In this study, we are focused on the individual level fairness. But before its definition, we need to define counterfactual twins. Let A is a protected variable that has finite levels. For each instance X, the set of counterfactual with respect to the levels of protected variable is called counterfactual twins. In other words, twins refer to what happens to another variable if we only change the sensitive attribute of x. The recourse action is individually or counterfactually fair if the recourse cost values are equal for all twins. Now let's examine fairness in linear schemes. We could obtain the explicit formula for twins by shifting the actual instance by using a Swan vector, which represents the first column of the interspace mapping matrix. If the first column of matrix S is orthogonal to omega, we have individual fairness. In other words, individual fairness implies that the classifier only depends on a subset of variables that are not influenced by the sensitive attributes and its descendant. We have same situation in a robust recourse. In linear schemes, the perturbation ball is an ellipsoid with twins as its center and have equal shapes. To find the best robust recourse, we need to move all ellipsoids to the positive region. We found out that for linear model we do not have fairness. Therefore, we are trying to address this issue. Combining fairness and robustness poses some challenge when applying previous definition and theories. We found out that the norm definition does not work well for categorical variables. So we extended the definition of counterfactual perturbation by using perturbation ball that is defined by metric or pseudometric. The fairness and robustness has similar notion. Each of them is achieved by similarity between counterfactual of x. Fairness is typically defined with respect to the categorical variables, while robustness is primarily defined for continuous features. Previous work utilized shift intervention to define the perturbation ball, but this approach is limited to the continuous variables. To solve this issue, we use metric instead of norms. In the presence of the categorical and continuous variables simultaneously, a new intervention definition is required to build counterfactual perturbation. The middle intervention is a combination of soft and hard interventions. The middle intervention fixes the values of subset of categorical features by some constant and perturbs the subset of continuous feature by additive intervention. Now we are ready to generalize counterfactual perturbation that involves both continuous and categorical variables. The figure shows a new definition for counterfactual perturbation ball. A challenge arises in balancing fairness and robustness, as fairness eliminates the cost difference between twins, while robustness only considers small distances between instances. In this issue, the dissimilarity function is key point. A dissimilarity function is a subjective measure based on our beliefs about objects. If we want to support sensitive attribute equality, it should influence the dissimilarity function definition. So we redefine the sensitive attribute from a metric point of view. Consider a categorical variable a with pseudometric d. A is called partially protected if there exist two levels such that their distance is equal to 0. If for all levels the distance is equal to 0, then A is called protected feature. The impact of a new definition can be seen in this figure. Using L2 norm for all variables causes non-symmetric perturbation around the twins. However, by using trivial pseudometric for sensitive attribute and L2 norm for continuous features, we have a symmetric counterfactual perturbation. The new definition ensures that the counterfactual perturbation is symmetric with respect to the sensitive attribute. Therefore, when we can find the recourse cost, this cost is equal for all levels of the sensitive feature. This is the main idea of new definition of adversarially fair robust recourse problem. In this setting, individually fairness can be seen as a special case of adversarial robustness, especially when we set delta equal to 0. Thank you for your attention.